Hello everyone. So, uulitin ko lang ulit yung report ko mula sa simula para tuloy-tuloy din yung discussion natin and mas lalo nyo maintindihan. So, ito yung pangalawang topic sa um, nire-report namin which is phenols. So, yung phenols is an organic compound containing a hydroxyl group that is directly attached to a benzene or aromatic ring. They are white crystalline compounds and also known as carbolic acid. They follow the rules of naming aromatic compounds, but instead of using benzene as a base name, we use phenol. So for example, the structure, we have a phenol as a base name tapos bromo yung substituent natin nasa carbon 2 siya kasi ito yung carbon 1 natin kung nasan yung OH tapos carbon 2 naman kung nasan yung bromo. So ang IUPAC nomenclature niya is 2-bromophenol. And kung nare-recall nyo, yung mga the substituted benzenes, they are named or they can be named using the ortho, meta, and para prefixes. Although hindi yun IUPAC. So, kung namali kayo sa pre-test, yung IUPAC natin ay yung gumagamit tayo ng locals. So, ito, since it's a one-to substitution, we use orthobromophenol, which is its common name. The second structure naman, we have here a nitro substituent in O2. So, ito 1, 2, 3. 1-3 substitution. So, IUPAC niya 3-nitrophenol. Tapos, ang common name is meta-nitrophenol. The fourth structure, we have an ethyl group na nasa, or rather the third structure, na nasa carbon 4. So, ano niya, IUPAC is 4-ethylphenol, pero ang common name is para-ethylphenol since 1,4 substitution. Meron din tayong tinatawag na methyl phenols kung saan ang kanilang substituent ay methyls. So, they are commonly known as cresols. So, nagkakaiba-iba lang sila sa prefixes ng ortho, meta, and para. So, dito, since naka-ortho to, so orthocresol. Meanwhile, meron namang benzene diols kung saan yung benzene natin contains 2-hydroxyl group. So, hindi na tayo gumagamit ng phenol as a base name, but rather, nagiging parent natin dito yung alcohol, so diol. At yung common names nila iba-iba, so much better na kabisaduhin. Kagaya na to, yung benzene 1,2-diol ay catechol, benzene 1,3-diol yung sorcinol, benzene 1,4-diol ay hydroquinone. In terms of the physical properties naman ng phenols, they are characterized to be weakly acidic. This is due to the presence of hydroxyl group. So, we can compare phenol and its equivalent alcohol, yung cyclohexanol. Pero makikita natin na or mababa yung pKa ng phenol as compared to sa cyclohexanol. So, phenol is more acidic than cyclohexanol. Bakit nga ba? So, first factor nito ay yung phenol kasi meron siyang resonance structure. So, itong lone pair ng oxygen can delocalize, leaving oxygen to be positively charged. Kaya mas madaling mag-abstract ng proton kasi nagiging electron hungry yung oxygen natin. Tapos, ito meron tayong negatively charged dito. So, nagkakaroon ng charge separation kasi may positive tas negative, which is moderately stabilizing lang. As compared din naman kapag piniprotonate natin yung phenol natin at nag-phenolate ang ion, nawawala yung charge separation na to kasi ang nagiging charge na lang natin ay negative na nagsispread out lang dun sa kabuuan ng structure. At yung phenolate and ion is more stabilizing than the phenol resonance structure. Dito sa cyclohexanol kasi wala tayong resonance dito. So, second factor pala is yung S character. So, yung phenol natin is sp2 hybridized. Ito. Ito naman ay sp3 hybridized. So, the higher the S character, since sp2 to mas mataas yung S character, the more acidic yung molecule natin. So, second is they have high boiling points. In comparing phenol and toluene na may magkalapit na molecular weight lamang, makikitang mas mataas yung phenol. This is due to, of course, the OH group na can form hydrogen bonding with other phenols or water. Kaya soluble din siya sa water because like dissolves type. Tsaka kailangan natin ng higher temp in order to break the hydrogen bonding. So, pangalawang factor din pala sa pangatlong factor na pala to sa acidity ng phenol, yung substituent effects. So, kung nare-recall nyo, sa aromaticity, meron tayong ortho and para directors and meta directors. Itong ortho and para directors, sila yung mga electron donating group. They activate the ring towards electrophilic aromatic substitution. Yung meta directors naman, sila yung mga electron withdrawing group. Dinada-activate nila yung ring towards that reaction. So for example, dito meron tayong methyl group, may methoxide tayo, tapos may chloride. They are all example of EDG, electron donating groups. Tapos makikita natin yung pKa nila mataas, which means mas napapababa nila yung acidity nung phenols. Kasi nagdo-donate sila ng electron towards dun sa ring. Ang gusto nga nito ay maging parang positively charged, di ba? Para ma-abstract yung proton. Ito kasi, yung electron density napupunta dito. So, mahirap mag-abstract ng proton. As compared naman dito sa nitro. So, electron donating group sila. So, kapag padagdag yung EDG natin, mas tumataas din yung acidity. Mas bumababa yung pKa, tataas yung acidity. So, kung mapapansin nyo rin pala, yung nitro, nasa ortho and para lang sila. As makikita natin sa previous slides. Ito. So, kapag nag-delocalize yung electron, nandun na sila sa ortho and para sites. Parasites. Okay, parasites. Nandun na sila sa ortho and parasites. Kaya yung hydroxyl group, siya ay ortho and para directing group. Kasi, na-enable niya yung electrophilic aromatic substitution dun sa ortho and para na location ng sa ring. Ayan. So, punta naman tayo sa synthesis. So, ito, na-discuss na to ni Nelson nung face-to-face. Di ba, meron tayong aminobenzene, tapos magre-react siya with nitrous acid to form this arene diazonium salt na in the presence of copper oxides, tsaka copper 2 plus and water will yield phenols. So, ang mangyari lang dito, ito yung amino group, papalitan lang nitong OH group. So, for example, ito, ano yung magiging product? Ito kasi kapag pinagsama mo itong sulfuric acid tsaka yung sodium nitrite, magiging nitrous acid lang to. So, ang magiging product nito, ito lang. So, hindi niya maapektuhan yung ibang substituent. Pupapalitan lang talaga ng OH itong NH2 natin. Sa industrial synthesis naman, meron dalawa. And itong first one is yung pinaka-old process of synthesizing phenols, which is known as the dope process or the hydrolysis of chlorobenzene. Ito, meron tayong chlorobenzene reacting with 2 moles of sodium hydroxide in high pressure at 350 degrees Celsius na magpaproduce ng sodium phenoxide. Then this sodium phenoxide will undergo acidification using hydrochloric acid to yield phenols. The second naman is from cumin hydroperoxide. Ito na yung kadalasan ginagamit ngayon to synthesize phenols. It is the conversion of benzene, tsaka propene, to phenol, tapos acetone. So yung product nito, phenol and acetone. Then it is a 3-step mechanism reaction. Meron tayong Friedel-Crafts alkylation, oxidation of cumin through radical chain reaction, tapos hydrolytic rearrangement. So, isa-isayin natin. So, sa Friedel-Crafts alkylation, iba to sa Friedel-Crafts acylation kasi alkyl group yung ina-add natin dun sa aromatic ring instead na acyl group. So, itong alkene group natin will protonate. Ayan. So, pupunta yan dito sa O, yung negative charge. Maging negative charge yung O, tapos makaka-produce tayo ng isopropyl cation. Tapos, ayun na, mag-electrophilic attack tong si benzene, das isopropyl cation to yield this intermediate which is called as arenium ion. Tapos, itong dihydrogen phosphate natin in order to, para mabalik yung aromaticity, kasi hindi na to aromatic eh. So, mag-abstract siya ng proton, tapos mag-form ulit yung double bond. So, ito na yung magiging product natin, yung isopropyl benzene. Tapos, isopropyl benzene will undergo radical chain reaction. So, for the chain initiation, di ba may tatlo yan? May initiation, propagation, saka termination. Dito, included lang initiation, saka propagation. So, sa initiation, meron tayo yung radical initiator. Kaya mag-cleave hydrogen bond. Tapos, mag-yield ng tertiary radical na stable. So, in radical form ng oxygen, ayan, magpo-form ng bond, tapos ito yung magiging product, and mag-protonate yan to produce this uh, cumene hydroperoxide. Ito na yung gagamitin natin to synthesize phenols. For the last step, yung uh, cumene hydroperoxide natin magpo-protonate, magre-react siya dun sa hydronium ion para mag-protonate. Tapos ito yung mag-produce natin. So, mayari dito. Ito si water, pwede na maging mag-leave kasi good living group na siya. So, kapag nag-leave yan, magiging positively charged to oxygen natin. So, para magiging cationic oxygen siya. And this phenyl group, may tendency sila to migrate. Tapos doon sila kakabit sa oxygen. So, ito yung magiging product natin. Ito si phenyl group, nakakabit na sa oxygen instead nandito sa isopropyl. Tapos si isopropyl natin magiging cation siya. Tertiary cation. Carbocation. Tapos yung, uh, ayan, si H2O kakabit lang doon. Hanggang sa may yield yung acetone and phenols. Sa reactions naman ng phenols, meron siyang parang three kinds. Oh, yep, it's three kinds. Meron as acid, yung yung reaction ng OH group ng phenol, tapos reaction ng benzene group ng phenols. So as acids naman, sa acid-base reaction, phenols is a stronger acid than alcohol. Kaya ang reaction niya with a stronger base ay uh, mas gusto, kumbaga, mas nagpo-forward talaga yung reaction niya with a stronger base as compared sa alcohol. Kaya yung phenols, nagdi-dissolve kasi siya sa sodium hydroxide, yung alcohols hindi. Kaya madidistinguish natin yung dalawa in terms of their solubility sa sodium hydroxide. Kapag yung phenols naman, hindi sila soluble sa sodium bicarbonate, pero yung mga carboxylic acids, soluble sila. So, ayun din yung pwede natin magamit. Yung solubility din nila sa sodium bicarbonate pwede natin magamit para ma-distinguish natin yung phenols sa carboxylic acids. So, the next reaction is focused on the phenols OH group. So, ang una nito is reaction with acid anhydride. Tapos, ito naman yung acid halide. So, nandito. Nangyayari is formation of phenyl ester. Itong si phenol natin will deprotonate siguro using the base. Magde-deprotonate siya. Magiging phenolate an ion to, magiging negatively charged tong O natin. Tapos, di ba yung anhydride natin, ganyan. RO, O, tapos R. Ayan, so ang mangyayari dito, kumbaga para lang siya mag-cleave. Ito, mag-cleave lang yung banda yan. Ito yung mag-cleaving, itong part na to, yung magiging anion. Tapos, itong part na to, yung parang i-a-attack yung phenolate natin. Parang ganyan, mag-a-attack siya doon sa carbon with carbon. Ganun. Tapos parang, kumbaga mag-leave to. Tapos, matitira na lang, ay, ito, magiging phenyl ester siya. Tsaka, itong, itong anion na to na kapag pin-protonate mo, pwede siya maging carboxylic acid. Ganun din yung parang mechanism niya with acid halide. Ito yung phenoxide ion, kunyari, negative na to. Wala na tong H. Kaya attack niya to. Siyempre yan, ganyan. Tapos kapag bumalik yan, di ba? Parang sa second step, kapag bumalik yung O doon sa, I mean yung oxygen, I mean yung electron doon sa O. Tapos yung double bond. Parang maglilib na si Cl, di ba? Ganyan. Naiintindihan mo. Sorry. So, ayan. Maglilib na si Cl. So, ang matitira, ito na lang. Yung ROOR, tsaka yung phenyl group. Tapos, ito yung leaving group natin, si chlorine. Which is also called as acylation of phenols. So, second naman is Williamson ether synthesis. Ang mape-prepare naman natin dito yung Aryl ethers. So, yung phenol natin will react with a base to yield phenolate an ion. So, parang nag-deprotonate na siya. Tapos SN2 reaction, will attack yung alkyl group. Tapos mag-link tong X natin to form this product, Aryl ether. Ayan, gaya na itong example na to. Ito na yung pangatlo, reaction ng phenols, which is yung reaction ng phenols benzene rings. Diba sa aromaticity lesson, may mga electrophilic aromatic substitution reaction ng benzene ring. Ito na yun yung mga bromination, sulfonation, nitration, iba pa. So sa bromination, it does not require Lewis acid. So in its general reaction, we have here 3 moles ng bromine. Tapos, di ba ang OH group is an ortho and para-directing group. So, yung substitution ay exclusive lang doon sa ortho and para na location ng sa ring. Wala tong, wala tong metal group. Ayun yung magiging product niya. Kapag ano. Pero, pwede rin na mag-monobromation, pero using ano siya, in the presence of carbon disulfide. Para, tawag ito, to reduce yung electrophilic reactivity ng bromine. So, ang major product na mabubuo sa monobromation is yung para-bromophenol as compared dun sa ortho-bromophenol. The second is nitration, which is reaction of dilute nitric acid with phenol. Parang mixture of products ang mabubuo dito. Meron tayong ortho, tapos para. They can be separated by steam distillation, pero yung ortho, yung more volatile because of intramolecular H bonding. Yan, pwede siya mag-form ng hydrogen bonds dito. Tapos, yung para-nitrophenol naman less volatile kasi intermolecular H bonding na yung kaya niyang ma-form. The third one naman is sulfonation, which is the reaction of phenol with concentrated sulfuric acid. Sa sulfonation, meron tayong dalawang product which is under kinetic control at thermodynamic control. Ito yung binabanggit ni Sir JD ng face-to-face. Na yung kinetic product is faster to form but not that stable. And then yung thermodynamic product, sila yung magbagal yung formation pero stable naman. So makikita natin dito yung mga ortho talaga. Hindi talaga sila stable or may lower stability drag as compared dun sa mga para substituted phenols. So the fourth one is the Colby reaction, which is carboxylation of phenols. Carboxylation, nag-add tayo ng carboxylic acid sa phenols natin. So, synthesis siya ng salicylic acid ng phenols. Ito yung phenolate and ion natin mag-react sa carbon dioxide na nag-aakas electrophile. Tapos, ito, non-aromatic to. So, mag-tautomerize siya para mabalik yung aromaticity. Tapos, magiging sodium salicylate and mag-protonate. Ito yung mag-form salicylic acid. Ito may carboxylic acid na siya. Tapos, yung salicylic acid pala, pwede siya mag-react with acetic anhydride to form yung acetyl salicylic acid or yung aspirin. Yung reactant sa Claisen rearrangement, yung allyl phenyl ether, can rearrange to form a phenol or specifically yung ortho-allyl phenol. So, concerted reaction siya, tsaka intramolecular. So, yung bond breakage and bond formation happen simultaneously and it is within the compound only. So, ayan. Bale, 6 electrons yung dito. Naglilipat-lipat, nag-rearrange. Nagkikita ay tautomerization to form this ortho-allyl phenol. So, another example na nag-undergo na Claisen rearrangement yung allyl phenyl ethers. So, ang form naman dito, instead of phenols, aldehyde. So, Claisen rearrangement ay under siya ng pericyclic reaction. So, might as well i-discuss na rin kahit paano to review. So, pericyclic reaction, meron tayong co-rearrangement, tsaka Diels-Alder. So, sa co-rearrangement, ang kinaibahan nito sa Claisen, meron tayong 1,5-diene dito. So, 1, 2, 3, 4, 5. Ito, 1,5-diene na nagre-rearrange to form this product. Sa Diels alder naman, meron tayong diene, tapos dienophile. And then, ang one characteristic ng Diels alder ay makakaroon tayo ng 6 carbon ring. From this diene and dienophile, nagiging 6 carbon ring siya. So lastly, for my topic, ketones. So yung ketones natin undergoes reversible oxidation reduction reaction. For example, yung hydroquinone natin, yung 1,4, yung benzene 1,4-diol. Kapag na-reduce siya, nag-add tayo ng 2 electron, magiging para-benzoquinone. Tapos kapag na-oxidize naman siya, magiging hydroquinone. So yung reaction na to are used for enzyme catalyzed transport of electrons. An example ng uh, organic component nag-undergo ng ganitong reaction is yung ubiquinone, which is known as coenzymes Q or COQ. So they are found within inner mitochondrial membrane. So, ayan, kapag na-oxidize siya, magiging ubiquinol yung hydroquinone 4. Tapos, kapag na-reduce siya, babalik siya sa ubiquinol. Yun lamang po sa aking report. Thank you sa pakikinig.
So, now that we're done sa phenols and amines, actually, let's head over sa aryl halides. So, aryl halides are very easily distinguishable since their structures may be composed of a halogen attached to an aromatic ring. So, aryl halides are known to be very resistant sa nucleophilic attacks, both SN1 and SN2. This is because of three specific reasons. So first, for SN2 reactions, this is prevented by the presence of the benzene ring. Since for SN2 reaction to occur, there needs to be a nucleophilic backside attack. Now, a nucleophilic backside attack requires that the nucleophile attaches itself to the carbon 180 degrees relative to the leaving group, in this case, our halide. However, this is difficult for the nucleophile since um, the planar geometry ng aryl halides natin would mean na the benzene ring would make the backside attack difficult due to static hindrances. Yun. Following this, SN1 reactions are prevented naman since for an SN1 reaction to occur, there needs to be the formation of a phenylcation. However, phenylcations are in nature very unstable. So, yun. And lastly, the aryl halides also have shorter and stronger carbon-hydrogen bonds. So, shorter because as meron siyang sp2 hybridization ng yung carbon. And this means na the distance between the electrons of the nucleus are actually shorter. Yun. And in addition, resonance gives the carbon-hydrogen bond a double bond character, meaning the bonds are actually stronger than the usual single bonds. Yun. Now, shorter and stronger carbon-hydrogen bonds make nucleophilic attacks less likely since for it to occur, um, it would require more energy than it would sa ibang functional groups. Yun. Now, despite saying that, that doesn't necessarily mean na aryl halides do not react in any way at all. So, dito na pumapasok yung nucleophilic aromatic substitution which can occur in three different ways. So, first is yung SNAR mechanism natin. Now, SNR mechanism is actually an addition elimination mechanism, meaning it involves first step, which is an addition reaction, followed by yung elimination. This occurs in the presence of a strong electron withdrawing group that is ortho or para to the halogen atom. This makes it more susceptible to nucleophilic attacks since yung strong electron withdrawing group will actually withdraw electron density away from the ring, making it more electrophilic. Yun. So, as we can see sa tatlong example natin, an increasing number of strong electron withdrawing group on the ortho and para position actually reduces, in this case, the temperature at which the reaction occurs, since less and less energy is required for the reaction to proceed. And lastly, for SNAR mechanism, this involves the formation of a mesenchymal intermediate. So more on that later. Let's first focus sa mechanism niya. So for this specific example, um, first is yung addition ng hydroxide ion natin resulting in the formation of the carbon ion, which is yung mesenchymal intermediate nga natin. Now, to stabilize itself, um, the chlorine is eliminated, so resulting in the formation of our 4-nitrophenol. Ito na yung pinaka-product ni SNAR mechanism. However, further addition of hydroxide ion results in the deprotonation ng phenol, resulting in the um, formation of an anion, in this case, for nitrophenolate anion. Yun. So, the Meissonheimer intermediate, why does it form? So, similar dun sa aluminum ion, this manages to form due to resonance. So, resonance makes it stable enough so that it can form on its own before siya mag-opposite sa ibang reaction. So, as we can see, the third structure from the left is especially stable since the negative charges niya are both on oxygen atoms. So, yun, if an arynium ion is a carbocation, Meissonheimer intermediate is an carbon ion, so negatively charged. Okay, so moving on sa second reaction for the nucleophilic aromatic substitution is yung elimination addition mechanism. So yung una, addition elimination, ito naman elimination addition. So first step is elimination, followed by addition. Yeah. So this occurs under highly forcing conditions. It's either by very high temperatures or in the presence of a very powerful base, usually liquid ammonia. This also involves the formation of a highly stable intermediate, which is a benzene or dihydrobenzene. So, ito, two examples, chlorobenzene and bromobenzene. The elimination addition mechanism for chlorobenzene is actually done at high temperatures. As you can see, for the reaction to occur, it needs to be at a temperature of 350 degrees Celsius. For bromobenzene, however, kailangan mo lang is very strong base. In this case, is liquid ammonia. And so you can see, by the presence of the liquid ammonia, doesn't have to be at high temperatures. It can occur even at very low temps. So, more on the mechanism. The reaction begins with the deprotonation of the aryl halide. So, The deprotonation results in the aryl halide acquiring a negative charge. This negative charge stabilizes yung inductive effect ni bromine, making it a good leaving group. So as bromine leaves the structure, mhm, the formation of a triple bond is allowed. So resulting in our intermediate na benzene, sorry. Now, since benzene is highly unstable, this means that it is also highly reactive. It would actually react with any nucleophile present sa solution natin. And since liquid ammonia ang gamit natin, our nucleophile in this case would be the amide ion. So the amide ion attaches itself to the benzene. And this could actually attach sa either of the carbon na connected by the triple bond. So it could be sa taas or sa baba. And since this would still have its negative charge, uh, this would go on to be protonated by our liquid ammonia, resulting in the formation of aniline in this case. Yun. So, in that specific example, sa unang example na pinakita, the amide ion it can attach itself sa either of the two carbons that are attached by the triple bond. However, the presence of an electronegative group, in this case, the trimethyl group, it would prefer na it would prefer syempre yung more stable na structure. And since um the more stable carbon ion would be that of which yung negative charge is closer dun sa electronegative group natin, mas prefer in this case na NH ni amide ion natin to attach itself to the carb in the position that is meta to the trifluoromethyl group. So for this specific reaction, first, again, the protonation ng aryl halide natin, then stabilization ng halogen atom, displace chlorine, resulting in it being a stable living group. Resulting in its stabilization, making it a good living group, allowing the formation of the triple bond. And yun nga, then is the addition of our amide ion, in which case it will attach itself in a way na mas malapit yung negative charge natin dun sa electronegative group. Then further protonation would give us our product. Yun. Now, moving on sa last reaction for non-levophilic aromatic substitution, which is phenylation. Now, this involves also the use of a benzene intermediate in the formation of carbon-carbon bond. So, essentially, yung first half nung second reaction natin ng elimination addition, gagamitin din dito sa phenylation. Now, this is a useful complement to alkylation process of acetoacetic and malonic esters. So, brief example ng mechanism na would be, let's say, the alkylation followed by the elimination ng aryl halide natin of alkylation ng either acetoacetic or malonic esters natin with the addition of the elimination of our aryl halides would result in the phenylation of diacetoacetic and malonic esters. Now, moving on to the spectroscopic analysis of both phenols and aryl halides for the infrared spectra. This is characterized by the OH stretching in the 3,400 to 3,600 uh, region. Excuse me, which is the characteristic absorption of benzene rings. So for the spectroscopic analysis of both phenols and aryl halides for its infrared spectra, it is characterized by the OH stretching in the 3,400 to 3,600 region, and is usually observed to be broad. And in addition, it also shows characteristic absorption of the benzene ring. So usually in the regions of 1,600 to 1,000, 1,600 and 1,500. Yeah. Next is for the H&M spectra. So the audio signal is strongly affected by the concentration of the phenol sa sample natin. And in addition, the aromatic protons for both phenols and aryl halides gives signals in the delta 7 to 9 region. For CNMR spectra, so carbon atoms of the aromatic rings appear in regions delta 135 to 170. And for its mass spectra, so it often displays a prominent molecular ion peak. And since there is a benzene hydrogen present in phenols, this can result in the product in the formation of M-1 peak that is taller than the M plus peak. So that is all for this for our report. Thank you.